Hello, we're now at the last video of this section, dbus communication. In the previous video we looked at handling device files. In this video we'll first understand dbus and learn to control service acquisition with SELinux. Finally, we'll look into governing message flows. The dbus daemon provides an inter-process communication channel between applications. Unlike the traditional IPC methods, dbus is a high-level communication channel that offers more than simple signaling or memory sharing. Applications that want to chat over the dbus link with one of the many dbus-compatible libraries, such as libdbus, sdbus, which is part of systemd, gdbus, and qtdbus. The dbus daemon is part of the systemd application suite. Before we move further, let's first understand dbus. Linux generally supports two dbus types, system-wide and session-specific dbus instances. The system-wide dbus is the main instance used for system communication. Many services or daemons will associate themselves with a system dbus to allow others to communicate with them through dbus. The session-specific dbus is an instance running for a particular logged-in user. It's commonly used by graphical applications to communicate with each other within a user session. Both dbus instances are provided through the dbus daemon application. However, the system-wide dbus will run with the --system option, whereas a session-specific instance will run with the --session option. Applications register themselves against the dbus through a particular namespace. Conventionally, this namespace is based on the domain name of the project. For instance, systemd uses the org.freedesktop.system1 namespace. You can find more information about this at this website, whereas dbus is at org.freedesktop.dbus, which you can find at this web link. For instance, to read all properties exposed by the hostname service, we call the org.freedesktop.dbus.properties.getAll method of the object bound at org.freedesktop.hostname1, provided by org.freedesktop.hostname1. We pass on the org.freedesktop.hostname1 string to this method. So, let's execute a few lines of command for this. Let's press enter. Here's what it returns on the execution of this command. Cool. Now, let's move on to controlling service acquisition with SELinux. The dbus application, like systemd, will query the SELinux policy to identify whether a particular operation is allowed. Again, it's the dbus application itself that enforces the policy, not a Linux kernel subsystem. The first control that administrators can enable within dbus is to ensure that only well-established domains can acquire a particular object within dbus. Without this control, malicious code could register itself as being org.freedesktop.login1, for instance, and act as a system daemon on the bus. Other applications might mistakenly send out sensitive information to the application. Applications store this policy information in files hosted in the etc/dbus-1/system.d path. Now, for instance, let's check the policy snippet installed which the login service has. So, here's the command which you need to execute for it. Let's click enter. On execution of this command, it returns the send destination, send interface, and send member. As the login daemon runs in the system_login_d_t domain, we could enhance this configuration with these lines of code. dbus will then check whether the application, which we presume is running in the system_login_d_t context, has the acquire svc permission of the dbus class against the system_login_d_t context. By default, the SELinux policy does not have this permission, and as such the registration fails. Here's how you'll get the permission denied message on your screen. In the audit logs, we notice that we have this denial. When we add this SELinux policy rule, the registration of systemd-login will succeed, as expected. By limiting which domains can obtain a given service, we ensure that only trusted applications are used. Non-trusted applications will generally not run within the domain of that application, even if they receive the root privileges. Administrators can enhance this dbus configuration without having to alter existing configuration files. For instance, the previously mentioned SELinux-governing bus config snippet could very well be saved as a different file. Before we end this video, let's look into governing message flows. A second control that dbus validates is which applications are allowed to communicate with each other. This is not configurable through the service configurations, but is a pure SELinux policy control. Whenever a source application is calling a method of target application, dbus validates the send_message permission between the two domains associated with the source and target applications. For instance, communication over dbus between a user domain, that is sysadmin_t, and service domain, which is system_logind_t, will check these permissions. If these permissions are not in effect, then dbus will not allow communication to happen. If at any point the application context cannot be obtained, which is not possible within Unix domain sockets, but might occur if dbus eventually supports other communication approaches, then the dbus context will be used. Great! In this section, we started out with an introduction to systemd and a strong focus on the service management capabilities that systemd offers. We learned how to start a service with a custom SELinux context, as well as how additional files can be properly labeled upon boot. Other systemd capabilities and services were touched on as well. We saw how SELinux contexts are registered as part of the systemd journal, and how to query for events using this context. Journal daemon integration with the SELinux troubleshooting daemon was covered as well. We learned how systemd supports containers and what administrators can do to fine-tune the SELinux context associated with the container. Finally, we took a brief look at udev and how its rules can be used to support administrators in managing devices. We finished the section with an introduction to dbus, how SELinux can be used to control the association of applications within services, and how dbus uses the send message permission to validate communications across its channels. In the next section, we'll learn how the SELinux policy can be tuned, and even how custom SELinux policies can be developed and loaded.